Welcome back. The agenda for today is we're first going to start reviewing things that we have covered. This will help you with the quiz. Sorry. Switch to short content. Okay. This will help you with the quiz and also kind of understanding the topics that we have discussed. There are lots of different things. I'm gonna talk about that first. So whenever we finish that, then we're gonna start talking about the new content. And as I said, the new content will not be part of your quiz one. Few quick logistics before we get started. Your computer assignment 1 is due this Sunday. It's very helpful for your quiz. Unfortunately we cannot extend the deadline. At best case, we can give you an additional day on Monday. If you cannot finish it, then you can let me know and we can try to see if there's you can submit it late with some penalty. Penalty would be probably like 30% to 50% depending on the day that you're gonna submit it. But make sure to actually do it because that's actually very, very helpful for your quiz as well as the process that you're testing your knowledge about that. And then, as I said, you need to submit your project to Gradescope. You can use different. You can submit it as many times as you want. One thing that I've realized is don't zip your file and upload as a zip file because it's not going to work. Yeah. Yes. Is it better now? No? Is it better? Okay. So do not try to zip, don't zip your file and upload because that will create compiler errors. Another thing that you can do is if your code doesn't run and you will have some compiler errors, you can message me and I can check the compiler error for you and send it back to you. But the first 3 tests is essentially the same test that you can run locally to see how your code works. And then the fourth part is kind of like similar to the third test. It's like a for loop that tests a bunch of things. And it's kind of like summing various different values, read and write from the memory and so on and so forth. So it's not like a crazy test. There was a bug in the test, unfortunately. My fault, and sorry about that. But it should be fixed now, so you should be good to go. Any questions about computer assignments? Yeah. Correct. So the question is about the PDF design. Yeah, if you are submitting the repo, then yeah. If you're submitting the repo, just make sure that it runs the test. Does it pass the test? Okay. Okay. So yeah. So all the files you want to do, make sure that included in upload them all together. Any other question? All right. We're not gonna give you another homework for this week since you need to work on the project, but definitely check out last year's homework and the quiz and the last 2-3 years actually. These are very important, especially since we didn't give you any homework on pipelining. Make sure that you check out the homeworks of previous years and maybe like try to solve it yourself first and then check out the solution and all. Because you will see similar questions in the quiz. Okay, so make sure to totally do that. And then if you have questions, ask us during the office hours or ask on campus wire. Okay. All right, so quiz 1, few logistics about that. It's in person next week here. We're gonna start it at the beginning of the class, and it's not going to be the full class, so it will be somewhere between 60 to 90 minutes. If you see that people need time, sometimes we also extend it a little bit more, like another 5-10 minutes. There will be a sign-in sheet that you need to sign your name and UID, so make sure to sign it. If you leave without signing, that consider that you're not in the quiz, so you're not gonna get the grade for it. So make sure that at some point during the quiz, you will sign a piece of paper, okay? The quiz, though, there will not be any paper copy for the quiz. I'm gonna share a PDF and link to a PDF, and then you're gonna use that, okay? So bring a device that you can find, like see a PDF. You're gonna display it on these 3 displays. So if you wanted to write down your answers in a piece of papers, you should be fine by seeing the kind of the questions on the displays. But if you bring a tablet or a laptop, would be more helpful for you, okay? What we have seen in the past is that unfortunately this room has Wi-Fi issues when there are lots of people trying to connect to the Wi-Fi. As a result, what we're gonna usually do is that we're gonna release the PDF sooner in the morning on the website. It's gonna be password protected. So during the quiz, I'm gonna just release the password. So check the website before coming to the class and make sure to download the file, the PDF file, so that then here you don't need your Wi-Fi, okay? You can use your laptop or tablet or any other electronic device to answer the questions. One thing you cannot do is using Wi-Fi or internet for searching and all. I'll describe that in the next slide. You have to scan your answers and upload it to Gradescope. So if you have a piece of papers, you need to take a picture of it and upload it. If you are using, your own laptop and all, that would be easy. You just save it as a PDF and submit. And as I said, there will be no paper copy for the exam, okay? So what is included in the quiz would be all the modules that we discussed so far. As I said, today we're gonna also talk about reviewing, so there's no new material per se. I'm gonna clarify a few things. So if you're preparing, what the hell is this? Hello. It's a prank or something. Anyway, so it will be everything that we started from the beginning up to today's review part. Whatever I say about branch prediction, not going to be included in your quiz, okay? So essentially your modules M1 to M7, that's including this review is M7. But as I said, this is not new material. You can bring any book, any notes, any file you want, okay? Make sure to download everything before the exam. The reason is that Wi-Fi is probably not gonna work for most of you here. And previous years, people are really frustrated and cause lots of anxiety and stress for them during the exam. So download whatever you need to download and have it on your computer, okay? Or your tablet or whatever, okay? If you need to bring copies, print and bring. I'm not a big fan of printing things, but if you want, you can print and bring things. Yeah. Yes, so the question is about for submissions. Yeah, for submissions, we will give you like 5 to 10 minutes to submit. And then we can allow you to, like the TA will be outside, so some people can go outside and upload their files. So there's like a little bit more room for uploading. And then it's a little bit staggered, right? So it's a little bit better, yeah. You can download anything. So the question is, can I download solutions or previous year homeworks? Yeah. Anything that already existed is fair game. You can download all of them. Okay. All right. So things that you are allowed or not allowed. So at the beginning, I told you at the beginning of the quarter, I said I may allow ChatGPT. Unfortunately, the answer is that I'm not gonna allow it. The reason for it is that there will be questions that are basic, and basic questions easily will be answered by ChatGPT. The reason that I want to ask you some basic questions is that for understanding the topics, you want to also understand some basics. So I decided not to use ChatGPT, although I really wanted to incorporate it. So as I said, you're allowed to bring anything you want, right? Any files, any books, any printed or digital content you want to allow, you are allowed to bring. You're not allowed to use any software or app. Okay, that means that you're not allowed to use any sort of writing assistant tools, anything that can answer, even if it's local. You can bring a calculator, whether from your phone or like a regular calculator. There's not going to be much like things you need as a calculator. There will be a few maybe equations, but simple like arithmetic. So it's not going to be crazy, computation. You're not allowed to use any internet in any shape or form unless you want to download your file or upload your file. So anything other than that is considered cheating. Okay, you cannot search. You're not obviously allowed to use things like ChatGPT and all, or anything like that. Okay, so searching is not allowed. And of course, you're not allowed to create new content in terms of posting a question somewhere or asking or chatting and or sharing it with the outside world and receiving information. And then, of course, you're not allowed to chat to each other and to discuss before or during the quiz. If you're not following this, that will be considered cheating, and we're gonna take proper actions based on what happens, and we're gonna report it. Okay. If you are a CAE student and your request has been approved, you can take the exam either over Zoom or at the CAE center. If you're on Zoom, you should connect to the Zoom and stay on the Zoom. And then only CAE students allowed this. So it's not like, if you don't feel well and then you email me and say that, yeah, I don't want to come in person. I want to do it at home. That's not going to be allowed. Only if you have an approved CAE request, then you can take it offline, take it online over Zoom. Otherwise, you have to be here. All right. And unfortunately, we cannot change the time. We cannot move it. Not for this exam, not for any other exam. The reason for it is this is a very large class. I cannot be selective on who takes exam at what time. I know many of you have different constraints. Some of you are traveling. Some of you have other exams and all those things. Totally understandable, but unfortunately, we cannot be selective because everybody has their own constraint. And we cannot like selectively, I'm not in the position to fairly judge this. And so I'm not going to do that. All right. Is there anyone else that has any questions or requires specific accommodations? Feel free to email me and I'm happy to help as much as I can. Is there any other final questions about the logistics of the quiz? All right. Yeah. The question is, are we going to lecture after the quiz? The answer is no. So Tuesday is just a quiz. But we're going to have lecture on Thursday, this Thursday and next Thursday. Feel free to use, question? Are there any makeup quiz? No, so there will be 3 quizzes and there won't be any makeup. What do you mean by makeup? Like if you miss this quiz? Yeah, it won't be, unfortunately, no, we're not gonna allow that. You have to schedule your interview. But yeah, just email me if special cases, email me and see what we can do. Feel free to use your office hours this Friday, Monday, and this Tuesday. If we need more office hours, we might add an additional office hours sometimes as well. Any final questions? Okay. So let's talk about things that we have learned so far. So the first step that we started with the role of the ISA, right? And we said that the ISA is the one that kind of like connects our software stack to the hardware, right? And in this class, we talked about RISC-V ISA, and we particularly focus on the base set, the actual RISC-V ISA. There's like tons of other instructions in the ISA as well. But we looked at the subset of the base set, which includes various different types of instructions. We talked about all of these and their formats. There are various different things to note, such as, some of them are using 1 source register, some of them using 2 source registers, some of them using destination registers, some of them don't. And then there's different functionalities, for example, different types of branches, different types of loads. Some of them are 1 byte, some of them are 2 bytes, some of them are 4 bytes, some of them are unsigned, some of them are signed. We have different types of shifts. There is arithmetic shift, and there is logical shift. There is shift left, and there is shift right. And then we have a bunch of different kind of R-type and I-type instructions. And then finally, we have the control flow instructions, such as JAL and JAL-R. And again, one thing that there was like lots of discussion on what is label and what is offset. And we told you that if you see kind of like a word, a text, that would be always your label. Anything other than that is an offset. Although here we show that we typically use JAL with label, you're also perfectly fine with using as an offset. So if you provide a number, that would be an offset. So keep that in mind. And also keep in mind that how we calculate kind of the last bit and then just kind of different ways of shifting things around for immediate. Yes, that's pretty much it that you need to know about these different instructions, okay? So make sure that you understand these instructions. Again, since this is open book, you don't need to memorize anything, but make sure that you fully understand different instructions, how they vary from each other, and how they're different, okay? Then we also talked about how do you translate this assembly instructions into a machine code, and we provided a table that shows that the same table that I showed you, how it's translated into machine code. And when you're doing your project, one thing that you learn a little bit better is how do you actually implement this in real hardware, what's the role of different parts. And as you can see, there's like, again, some instructions that do have RD, some of them don't. I think the most confusing part about machine code is the way that we encode the immediates. Some of them are fairly straightforward, but some of them are kind of concatenated in different ways. So you need to kind of reshuffle them back and reorder them back. So pay attention to that as well. And again, that's pretty much it with the instructions. And if you remember, I said that essentially RISC-V has this 6 different types of instruction, the R, I, S, B, U, and J. And again, you don't need to memorize this. The way that you understand which type this instruction is by looking at the structure. If I see this type of a structure, then this is an R type. If I see this type of structure, this is I type, and so on and so forth. This is mostly for kind of categorizing this type of instructions into groups. There's no significance about the difference between these different types of instructions per se. For hardware, they're all instructions that needs to be executed, but we kind of like put them in categories so that we can kind of like become more systematic when we're analyzing them. Yeah. So the question is that can we use software that converts decimal to binary and binary to decimal? If you're using a simple calculator, you can do that, yes. But you cannot write like you cannot use like online tools for that. Mm-hmm. Cool. So yeah, this was mainly your homework 1 and CA1, right? So probably that's where you're gonna practice this a little bit more. Then we talked about the execution model, and we said that, okay, we start with a high-level program. We use the ISA to create the assembly. We use this table to translate this into the machine code, and we put this code into our, what we call the memory or instruction memory. Then from now on is basically the CPU going to read these instructions one by one, and they're going to execute that. So we start talking about how do we designing this CPU, right? So this part that kind of reads these instructions one by one and run it. And we gave you the design of a data path and a controller. And we said that the data path and the controller also talks to the memory, right? So there's a connection between the controller and the memory. And there's also connection between data path and memory. We gave you the full design of 10 instructions. Again, this is not supporting all the possible instructions in RISC-V ISA, only supports that 10 instructions. In your homeworks, for example, you saw that we asked you to add support for this instruction or add support for that instructions. And what you had to do was changing various things. Sometimes you need to change the wiring. Sometimes you need to change to add additional units. Sometimes you just need to change the control signal. So mostly like, changing the ALU op or defining a new ALU op and so on. And sometimes you don't need to change anything at all. Sometimes, the design is sufficient to support that instruction, okay? But typically, like, changes are fairly minimal based on the design that we already provided. The reason that we provided that kind of 10 instruction was it was fairly covering all the different types. That's why if you add more instructions, we didn't like make any big changes. But in your homework, you saw that like we asked you to add 3 new instructions. And in your quiz, we might also ask you to add like a custom instruction or another known instruction. You have to be able to understand what is the role of each unit and how we connect these different things to create this. So if I gave you like an arbitrary instruction that does like very arbitrary things, you should be able to analyze what are the units that it needs, what are the operations that it needs, and being able to kind of add different units to your system, okay? Does anybody have any remaining questions about the data path and controller? Yes. Should be able to what? Oh, the question is about should be able to draw. So that was actually one problem that in the past people had. Last year we didn't had any question that was required drawing. The previous year we did. Probably the drawing should be simple, so you can probably just like copy it into like a PowerPoint or something and then add your kind of boxes. So that should be good enough if you're using only your laptop. But of course, if you're using tablet, it would be easy to draw. So it might be, there might be a question, but again, you can probably get away with just your laptop. Okay? Yeah. It's a 2-bit. So the question is about ALU op. ALU op is a 2-bit signal. That's why it's a little bit thicker, as you can see here, compared to these other guys. And this is, as you show, it's 3 bits. It's 4-bit signal, right? So ALU op is 2-bit and ALU control is 4-bit. So the question is, how come 7 bits goes in and then many bits coming out? Doesn't need to be, there's no reason that these things needs to be the same, right? So you can always generate more if you want to. You can extend things in combinational logic. So there's no issue of creating. Think about this as a lookup table that you can generate, right? So you can easily implement this like that. Yes?
So the immediate generator, have logic within it that helps it identify what kind of instruction type you have?
Yes, the question is about immediate generator and how it operates. So immediate generator is kind of completely combinational. As you can see, it takes the 32. Honestly, it doesn't need the whole 32. It actually needs less. But we can actually decide based on this 32 of which operation needs to be done. Sometimes it doesn't need to do anything if it's, let's say, an R-type instruction. So it checks the opcode first. If it sees that the opcode needs some form of additional operations, then it checks func3 and func7 it needs be, and then make a decision. So again, think about it as kind of a table with a bunch of different types of data that it can generate. And based on the opcode, you select which of, like, think about it like a mux, that the opcode basically goes here. You connect all of these things here, and then you select the one that you want to select out. That's the simplest way you can implement this. In reality, it's a little bit more complicated. Actually, in the book, they have the actual logic design of it if you're curious. But the simplest thing would be something like this. And then in your project, you probably also implemented somewhere like this, that you had like a switch case, and then you had different ways of generating your immediate generator. So that would be the kind of equivalent of that. Yes. Mm-hmm. So the question is about how do we find the path? of different instructions and how to compute the delays. So what we're gonna do is that you always start from a register and you end with a register, okay? So the registers that you have is this PC and this register file, kind of, okay? That's really what the two things that you want to start. So we typically start from the PC, okay? So we start from this point, and then again, if you see any wires that goes into any direction, you have to follow that wire, okay? So that's what you usually do. So when I start from here, of course, reading this PC might have some delays. This is the reading delays of any register. So that's the first number that you're gonna add. Then you're gonna follow different paths. So you're gonna see that, oh, there is a path here and there is a path here. You have to follow both of them. The problem with these systems is that you don't know which one is gonna be the longer, okay? If you have some intuition that one of them will be the longer, you follow that path first. But typically, you have to follow both paths. Another tricky things to know is that not all the units going to be used for all the different instructions, right? So for example, for let's say something like an add instruction, I'm not going to use this add, right? This mux not going to be used. It's always going to be this one. So I don't need to kind of like follow this path along because I know for the fact that this is always mux 0, which is the default value, right? So I'm not going to compute the whole path this way and this way for the add instruction. What I'm going to calculate is basically just going through this path, right? Because I know for a fact that this is not going to be used for add. But if this is a branch instruction, then I'll do that. So my suggestion is, if you see a question like this, generally try to first understand which unit's going to be used and which units are not going to be used. That immediately kind of take away lots of path for you, okay? Then you basically just need to add values, right? So for combinational logic, that's simple, right? So you just add these numbers along the way. For the mux, you have to see the three things, right? So these two datas and the selected of which one going to be selected. Between these two, you have to know which one going to be selected, and your delay would be that one, right? So you don't need to compute the delay for both. You will compute the delay for the one that is only selected, right? So that's one thing that you do. But you also need to kind of compute the delay for your selector. And again, especially if the selector is not the default value. If the default value is always 0, then you need to compute that. Otherwise, you can just go with this. Otherwise, you have to kind of see between this and this, which one is slower. The max of these two delays is the one that decides this. And since mux itself is a combinational logic, there is always a delay associated with the mux. Just passing through mux itself has some delay, okay? So that's it with the delays. Things that has like a combination of control logic and data path, again, you have to compute the max, right? See which one is the slower, and that will be the one that decides which one, what is the total value. Yeah. So the question is what makes a path critical? We don't know. So you compute all the possible paths for an instruction. The one that is largest, that's your critical path. So there is no notion of critical. All of them are path. When they say critical is the one that is like longer. Yeah. Uh-huh. 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 Mm-hmm. Yeah, the question is about the bypassing multi-cycle and the fact that you had an AND gate that was part of the memory stage. And if you want to bypass, what should we do with that? In order to be able to bypass, we need to change the logic completely. We didn't show that in the class. So that's why the question was more of a hypothetical question that if we could pass, would that give us any performance benefit? In reality, if you want to be able to pass, you have to add tons of control signals because then you need to kind of like, the same way that we did kind of the bubbling and all those things, we need to kind of do that. So we need to insert bubbles and all that. That's why multi-cycle is not really a very popular design in many systems. That's why we do pipelining, which everybody go to all the different stages. There's no bypassing of any stages. But instead, we kind of overlap the stages so that that's the way we're going to get the performance. Yeah. So the question is that for computing the critical path, is it a good idea to go through every component and try to see what is the max delay? Again, the easiest thing to do is that you don't make any assumptions. Try to observe all the paths and consider all the paths, and then you will see which one is going to be the maximum. But easier things to do is first eliminate the path that's not going to be used in this particular instruction. So some units not going to be used for some instructions versus some others are going to be used for the others. Right? Great. And then again, like the details of this design you will see in your project one, and that's again why project one is helpful. And one thing that we emphasize a lot is we want you to exactly implement this. For kind of running a sequence of instruction in RISC-V, there are many ways that you can do it. There are simple ways such as you take the instruction, you do all the operations at once, and then you print the result out. That's not what we want. We want you to kind of create some form of a function for each of these units and follow this controller data path behavior where you pass through the controller some signals to as the inputs of your functions, and based on those inputs, you make different decisions, okay? We are not trying to run like an efficient software. We are trying to simulate the behavior of the processor to learn that, okay? So it may not be the most intuitive way to solve this particular problem if you are, let's say, a software developer. But here, the goal is not like writing a very efficient software. The idea is that to be able to mimic the behavior of the processor. The most efficient way of implementing this is the processor itself that we already have. So there is no need for actually running these things. We just simulate this. And as I said, the reason that simulators itself is very important is that in real companies and when they are actually building chips, they're not going to just blindly design the chip and tape it out and then test it. They're going to run tons and tons of these simulations first in order to make sure that the design is performant and good enough. So for example, you need to decide how many register files do I need, what sort of branch predictor do I need, what sort of connection to these different units do I need, and so on and so forth. In order to understand that, that's exactly what they do. They write some simulator, some behavioral simulator that all it does is just measure the performance of the system. And again, all of these big companies are going to have like very, very sophisticated simulators internally that does these things. Okay, so you kind of like learn this process a little bit. And as I said, adding new components, new instructions, you should be able to reason about different units and their operations. And if I ask you to give me a new functionality, you should be able to think about what are the things I need to add to the systems to provide that functionality. And yeah, we already discussed the data flow for like things like load or branch and so on and so forth. As I said, most important thing is that kind of like identifying which units and which ports going to be used and not going to be used and what is like the path. And then the rest is just adding numbers together and making sure that you're not missing any logic here. Okay? So that was kind of it for the data path controller of single cycle. Then we start optimizing that, and that was kind of like the discussions of last few lectures. We start by like talking about what's the best way to measure the performance. And we told you about this iron law processor law, which is basically measuring the CPU time. And we want to minimize this, right? So lower is better. And in order to minimize this, we have 3 different parameters that we can optimize each one individually. Instruction counts would be more of algorithm level or compiler level. Cycle per instruction and cycle times is the ones that the computer architects can play with. And as I said, for single cycle, the cycle per instruction is always 1. But the IC and cycle time can change. And then when we go to the pipeline, we tend to kind of also make this almost equal to 1. But what happens is that my cycle times is almost divided by 5. And that's why I get 5 times improvement in terms of performance. That's kind of like this was for the pipeline design. Okay. And then we start talking about adding overlaps, in other words, adding pipelining. And we show that if I add pipelinings, I can basically break down my critical path into smaller units, right? So what used to be T seconds, if I add like, a register in between, now I can clock it at T divided by 2 seconds. If I add 3, I can do it ideally at T by 3, and so on and so forth, which we discuss also the difference between latency and throughput. And what we said is that by pipelining, we essentially also increasing our throughput by a factor of 3, because now I can overlap 3 instructions. So I can have 1 instruction here, 1 instruction here, and 1 instruction here. So that's why it's not just latency that's been improved, it's actually the throughput that's ultimately improving the performance of my processor. Then we start talking about the pipeline design, and this was kind of like our pipeline design. We talked about various different decisions and the fact that not all the signals in one unit are from the same. So for example, these guys are coming from here versus these signals are coming from here. So this one is in the decode stage versus this signal is technically from write back stage, and so on and so forth. And then about the control signals, we essentially pass the control signals through the pipeline registers as well. So they kind of like go through the stages to make sure that at every single clock cycle, we have the correct control signal for our design as well. And then we make those decisions such as like, we do the PC plus offset in the execution stage. We do the branch taken, not taken in the memory stage. We do PC plus 4 in the fetch state, and so on and so forth. So the kind of design decisions that we make in this design. Any questions about this one? Great. And the last thing that we talked about, and that was last week, was the problems that this system brings. And the main one was hazards. We had data hazard and control flow hazards. We also had structural hazard, which was not an issue in most cases. So we talked about these 2 types of hazard. The first one was a data hazard, which essentially was just raw data hazard, which was read after write, which if a reading an instruction, reading a register right after writing to it, and then there's not enough time or cycles between them, we're going to have this issue. And we said that we need 2 cycles in order to resolve this issue. The reason that we need 2 and not 3 was because of this half cycle thing, that we should be write in the first half cycle and read in the second half cycle. So these cycles, these instructions can be overlapped totally fine because we're reading in the second half cycles of this design. And then in order to fix this issue, we proposed 2 options. One was stalling, and the second one was forwarding. The stalling was very simple. It was basically just adding some no-op instruction or bubble instructions inside the system. We told you that you can do it statically by just changing the compiler and inserting this bubble instructions offline. Or you can also detect this during the runtime and insert the bubbles in the pipeline itself. So either of these 2 could work. And for example, you can add just 1 or 2. As I said, in worst case, you need to add 2 cycles of a stalling. In some cases, you just need 1. And then the third one is good because of the half cycle. So this is good because we have the half cycle property here. Okay. How do we insert the bubble instruction? The bubble instructions was basically by just adding this mux in our decode stage and then feeding the zeros to the controller. So all we need to do is adding this, what we call the hazard detection unit, which basically just reads the instruction types. And so the information from future instructions, the RD of future instruction, and RS1 and RS2 of the current instruction. If we detect that, then we're going to issue this control signal. that it will be equal to 1 when we detect a hazard, a raw data hazard. And what happens is that instead of passing through the actual controller, now we are passing through 0. So we're inserting the bubble, which is like an instruction with all zeros as the controller. That's all we need to do in order to fix this issue of hazard detection. The second thing that we need to do for the hazard detection is we need to freeze the fetch and decode states. So not only we need to insert the bubble to execution memory and write back, we need to prevent the fetch and decode from advancing. How do we do that? We add these two control signals called IFID write and PC write, which are write enables for these registers. So this register here and this register here are not going to be updating if this control signal is equal to 0. Okay? So we only write them if they are equal to 1. And this way, we always keep this instruction here and this instruction here. We only let them go when it's safe for these two instructions to advance, right? So that way, we make sure that we freeze fetch and decode, and we let the execution memory and write back to advance. And by advancing, we add and insert the bubble, which is basically just 0 signal, okay? So as I said, these are the main two things that we are really adding, this mux and then these two control signals here and here. And both of them are generated by the hazard detection unit, which is separate from the controller. You can think about this as part of the controller, but for modularity, we usually show it as a different unit in our system, okay? So as I said, there are two options. This was option number 1. A better option is forwarding. Forwarding gives us performance. The reason for forwarding that it works is that the data is produced here. So we can actually either forward it at the beginning of the memory stage, or we can forward it at the beginning of a write back stage. So we have two options of forwarding. And we can forward to the next instruction or in the next two instructions. So 4 different options that you have for forwarding. How do we implement the forwarding? We're going to add 2 new muxes in the execution stage. This mux is going to be controlled by this new unit called forwarding unit. Forwarding unit is basically just takes the RD of EX and RD of memory. It also takes RS1 and RS2 of the current instruction in the execution stage. And based on that, if it sees that these instructions are the same, it's going to issue this forwarding logic. And as I said, forwarding can happen from memory to the execution, or it could happen from the write back to the execution. And forwarding can also happen from RS1 or RS2 or both. So we can have 2 forwardings at the same time, or we can forwarding one from the memory and the other one from the write back. There are all these possibilities for forwarding as well, okay? Questions? Great. So this would be our data path with forwarding. And as I said, we forward either from memory or write back. We forward from RS1 or RS2 or both. So pay attention to that as well. This is kind of like a more systematic way of doing the checking. And the good thing about forwarding is that it prevents stalling. So we technically don't need to stall the processor anymore. But we said that that's actually not always true. Why? Because we have the load word instruction and what we call load use data hazard, which we only have the data at the end of the memory stage instead of having it at the end of the execution stage. As a result, I need to stall the processor. So this was one example that I have something like this, that I'm updating this X5, and immediately after I'm going to use this X5. And if you look at the timeline, the X5 will be available here, but I'm going to need it at the beginning of that cycle. So there's this problem of one cycle problem. In order to fix this issue, and as I said, there's no notion of half cycle in memory. I cannot finish reading memory in half cycle, unfortunately, because memory takes much more time than register file. In register file, I can do half cycle because reading from register file is quick, but reading from data memory is not quick. That's why it takes the full cycle for me to read from the memory, okay? So how do we fix this? We're going to combine forwarding and stalling. So we're going to stall for one cycle by inserting the bubble and then forward from the write back stage. So we cannot forward from here, but we can forward from here. And that's what we're going to do. What we're going to do during that cycle, we're going to insert the no op, obviously, right? And this would be the condition that we're going to basically check the IDEXRD and IFID and so on and so forth. And this would be basically the combination of all these things together. So I'm going to have a hazard detection unit that detects the load use data hazard. Sorry. And so this is basically for just detecting that we have a load use data hazard. And the rest will be basically taken care of by this forwarding unit. So if I have an RD of EM, so MEM or write back stage, and RS1 or RS2 of execution stage, the forwarding is going to forward. Otherwise, if you have a memory load use hazards, the hazard unit detection is going to stall for one cycle, then we're going to have the forwarding. So both things happens in our design when we have a load use. Make sense? Any questions? Great. Yeah, so to pay attention to kind of like the inputs again. And then again, outputs, the same story. When we are doing the stalling, we need to prevent fetch and decode from advancing in our pipeline, but we should let execution, memory, and write back to advance. So we insert bubble, but we don't let these guys to move forward. Okay? And then again, combining the two will be the forwarding and the hazard detection unit. Pay attention to the conditions and the signals that goes in and out. And then, yeah, as I said, the forwarding of these signals as well. Okay? Then we also had what we call the control flow hazard detection. The problem was that at some points we need to, while we are kind of like by default, we do PC+4, and we feed new instructions into our pipeline, there will be a point that we can no longer feed PC+4 into our pipeline. Instead, we need to jump over and do PC plus offset. So in order to fix this issue, again, we have two options. The option number one was stalling the processor to wait for the branch outcome to be known. The second option was a speculation, which means that we make a guess, and based on that, we continue. If we made the wrong decision, then there will be a mechanism to fix that issue. So speculation is not the same as forwarding, okay? So for stalling, we talked about two things. The first thing was how many cycles should we stall? And for that, we answered these three questions of 3 Ws. We found that at the beginning of the memory cycles, it's where we're going to find out that this branch is going to be taken or not. So basically, this control signal will be known at the kind of like somewhere in the middle of the memory stage, right? As a result, we need to stall for 3 cycles, okay? Because we know this once we are in the memory stage. Then we go to the second option, and that was, okay, let's say I don't want to wait for 3 cycles. Can I do better? And we start with like speculation or prediction. I said that there are 2 options. Either I can do always taken or always not taken. We went with always not taken because with always not taken, I can just continue PC plus 4. So in other words, I don't need the destination address anymore, which is much, much simpler thing to do. So I can just pretend that this branch never happened, and I just continue normally. And since most of my instructions are not branches, 80% of my instructions are not branches, that's great. And then those 20%, some of them are actually not branches, are not taken. So there is some improvement in our design. But then we had a big issue to solve, and that was we need to flush. For flushing, I gave you the design like this. So this was our original design. We're going to add this additional muxes that is going to flush our processor. So essentially, the idea of flushing was replacing an instruction with a bubble. So that was kind of like the key idea for flushing. And again, the flushing is done by the hazard detection unit. The hazard detection unit takes the input of the outcome of the branch. Once it knows that it made a mistake during the mem stage, it's going to issue this flushing instructions into the pipeline. Okay. Another optimization that we did, and again, we still need these control signals for not letting the system to advance, but we also need to add this additional muxes here. And we still have our forwarding and hazard detection for load use. So this is in addition to all of those things that we had. That's why we have like an OR instruction here. So pay attention to that. The last kind of things that we discussed last time was that I also don't like this 3-cycle penalty. Although I'm guessing, and I'm guessing most of the time is correct, if I make a mistake, I need to flush 3 instructions, and I don't like that. So what we do instead was optimizing this. And we optimize it and show that I can reduce this from 3 cycles to 1 cycle. How do I do that? By moving the branch resolving logic to the decode stage, right? So the things that we did was basically we moved things around by adding these units to our design. We add this comparator here. We add this add here as well. And this way, what we showed is that now I know that at the end of the decode stage, whether this branch is supposed to be taken or not taken. We still go with not taken strategy. So we still, if we see a branch, we're going to ignore. But the good thing and the difference between this design and the original baseline design is that now after the decode cycle, I know that whether this branch was supposed to be taken or not. So at worst, I just need to flush 1 instruction out of my pipeline instead of 3 instructions out of my pipeline. So huge improvement in terms of this, the penalty. There were questions about like how this exactly works. This is like a simple comparator. Remember, for branch, we were using ALU, but now I need to kind of replace that with a comparator, which basically takes these two RS1 and RS2 as the input, and then there will be a control signal that goes to the hazard detection that I didn't show in this graph. Okay, so that gives me this this improvement here. Okay, and again, so we resolve this at the decode stage and pay attention to the design strategies. Okay, and then this is our kind of like the difference between if I don't do any branch prediction and if I do branch prediction. So this is no branch prediction at all, and this is with the branch prediction. So you see that you're adding a lot of control signals in order to be able to address this problem. Okay. And then final thing that we kind of like very last thing that we discussed last time was, unfortunately, this new way of designing things creates a new hazard. And this is what we call a branch data hazard. That if we have a scenario like this, that if I write to X3, so if X3 is my RD, and immediately after that, I try to read that, I immediately try to read that. And by the way, this is RS in this instruction, but this is RD, so make sure that you're not confused here. So we will have a raw data hazard similar to the previous raw data hazards that we have. The difference, though, is that since I'm resolving the branch in the decode stage, I do this comparison during the decode stage, but my forwarding only applies to the execution stage. So my forwarding will not help me in this particular scenario because I read the registers and try to compare them during the decode stage in this case, but my forwarding only applies during the during the execution stage. So what should we do? And I told you that there will be a combination of forwarding and stalling. I'm going to break this down for you a little bit more. So first of all, there will be 3 scenarios, right? So if the RD is in the write back stage and your branch is in the decode stage, that's scenario number 1. Scenario number 2 is that your RD is in mem stage and your branch is in decode stage. That's scenario number 2. And scenario number 3 would be obviously if your RD is in the execution stage and your branch is in decode stage. Okay. So let's talk about each one by one. First of all, let's talk about this one and let's see if you can tell me what happens here. So if this thing that I'm showing you here, if this instruction is in write back stage, so this one is in the write back stage, and there are a bunch of instructions in between, okay? So there are some instructions in between, and then this instruction is in the decode stage. Do we have a raw data hazard? Yes or no, and why? Anyone? Yeah. Exactly. So we're not going to have a raw data hazard here. Why? Because of the half cycle. Because this one says that I'm going to write to X3, but since the write happens in the first half cycle and the read happens in the second half cycle, that immediately fixes the issue. So if there is a write back to decode, because of the half cycle, there is no stall needed. So there is no raw data hazard to fix in this particular scenario. Okay? So far, so good. But then we have memory to the decode stage. And again, remember that my forwarding logic was forwarding from memory to execution stage. But then now I need to read these two values here, and my comparator was here. So I need to, if I want to forward, I need to be able to forward to here. Okay? So I have two options. One option is that I can stall for one cycle, let this instruction goes to the write back stage, and I'm back to the write back to the decode. So if I have my instruction, my RD in the memory stage, I can stall for one cycle, the instruction goes to the write back, and I already told you why write back is not an issue. That's one simple solution. But that means that I'm stalling one cycle for every raw data hazard that I have for the branch. The second option, which is more involved option, is what if I forward to here? So essentially what I can do is that similar way that I'm doing forwarding here, I can forward here. So essentially what I'll do here is I have my register file here, okay? I'm going to read RS1 and RS2. Then I'm going to add a multiplexer here that takes this. And this value here is going to be coming from all the way from the mem stage. Okay? From the mem stage, I'm going to read the correct value and put it here. And I'm going to have a new forwarding, let's call it forwarding DEA. Okay? So essentially what I'm going to do, and then this value, and then let's say we have the same mux here. And this value is the value that's going to go through that comparator. Okay? So this way, I'm forwarding the correct value from the mem stage to my decode stage. So I add additional 2 muxes to my design to allow memory to decode stage forwarding. This is a new forwarding that I'm adding. And as a result, a new control signal. Okay? So going back to here, I'm basically going to forward from here to here. Okay? Something that I didn't have before. Why I'm doing this? Because if I have a raw data hazard between branch and instruction in the mem stage, I don't need to stall one cycle anymore. Okay? So this way, I forward to DE, and this means that no stalling anymore. Okay? Or if I don't really want to add this additional cost to my system, I stall for one cycle, it goes to the write back, and then write back already taken care of. Okay? There's obviously one big issue, and that is if I have a load use raw data hazard, then I cannot forward anymore. Because again, remember, load use data is available here and not here. So forwarding not going to help. So if I have a load use data hazard between the branch and a load, then I need to stall. So let this goes to the write back stage, and from there, I'm good to go. I don't need any forwarding anymore. Okay? So be careful. I can forward from mem to DE if this is like an R type or I type. If it's the load branch hazard, I cannot forward. I need to stall for one cycle, and then from write back, since we have a half cycle, it's going to fix it itself. Okay? And lastly, if I have an execution to the decode stage, this is the final issue that I'm going to have. And there I also need to stall for 1 cycle. Why? Because the data will be available at the end of the cycle. The data will be available here. So I cannot forward from here to here. Instead, I'm going to stall for 1 cycle, let this instruction goes here, and then I'm going to forward from here to here. So assuming that I have forwarding in the mem stage implemented, if I have an execution stage raw data hazard, I stall for 1 cycle, let the instruction goes to the mem stage, and then from mem stage, I'm going to forward. If I didn't have my forwarding from mem stage, then I need to stall for 2 cycles. I will let the instruction from execution goes to the mem and then goes to the write back, and from write back then I can let it to go. Okay, so to kind of like summarize, I'm going to quickly go over it again. If I have write back to decode, I'm good to go because of the half cycle. If I have memory to decode, I have 2 options. I can either stall the processor for 1 cycle, or I can forward. For forwarding, I need to add new logic. I need to add new muxes. With the current design, we cannot do that. We need to add more, okay? But if I have load use raw data hazard, I cannot forward anymore. So the only option that I have is stalling the processor. Then finally, for execution, there are 2 options. If I don't have the memory forwarding implemented, I need to stall for 2 cycles. If I have the memory forwarding implemented, then I stall for 1 cycle, let the instruction goes to the memory stage, and then I'll forward from the memory stage. Okay? So be careful about all these possibilities. So there's kind of various different possibilities depending on what you have. And what we can ask you is that, let's assume that we have this or not that, or we have this and that. There could be many, many different possibilities. You have to be able to parse them. Yeah. Yes. The question is, the general idea is that you can forward the beginning of cycle. Yes. Another question. You had a question? Uh-huh. Oh, for writing the code? So the question is, should I use ID or D? Yeah, either one is fine. All right, so that's it for the review. Hopefully I'll clear up things. And as I said, make sure to watch this video so it'll help you with your quiz. Let's have a quick break, then we're going to start a new topic. Any questions? Clear? All right, so we're going to start talking about branch prediction. We kind of started talking about it by talking about not taken, taken. Now we want to make it more advanced. The first thing that we're going to do is changing not taken to taken, and we're going to show you what are the things you need to do in order to achieve that. Then we're going to talk about what about we actually make this decision dynamically. So instead of always doing taken or always doing not taken, maybe I can do a better, more intelligent way of prediction, where sometimes we make taken, sometimes we predict not taken, and then we can interchangeably during the execution, we can change that. Okay? And as I said, this is not going to be part of your quiz. So whatever I say from now on would be part of your quiz 2, not quiz 1. Just be careful. Okay. So remember, there was 2 things that we are trying to fix, okay? The first one was reducing the miss penalty. That if we predict not taken, what can happen is that we need to flush things out. And I just showed you that how we reduce the miss penalty from 3 cycles to 1 cycle by moving all things. But as you saw, there are a whole bunch of other complexity, including the raw data hazard and load use hazard and execution hazard and all that. But we can fix all of that through adding more and more muxes and more complexity. And that's what most modern processor does. So far what we have is we have an always not taken system that the miss penalty for it is also 1 cycle. So in most cases, we just predict, like in all cases, we predict not taken. Some cases we will be wrong. And those wrong cases, we will miss 1 cycle because we need to flush 1 instruction, okay? And that was miss penalty. But another thing that we can do in order to improve our branch prediction is what we call miss rate. Miss rate means that out of the times that we see a branch and we make a prediction, how many times are we wrong? And of course, you want your miss rate to be 0, ideally. It's hard to achieve that. It's almost impossible. But at least you want to make it close to 0. And as you saw before, if you remember, I told you that like from instructions that we see, about 70% of instructions are actually taken. 70% of branches are taken, and only 30% of branches are not taken, which means that our miss rate is 70%, or accuracy is 30%, right? So we have a very crappy branch predictor because it only works 30% of the time when it sees a branch. We improve it by improve the miss penalty, so at least we are only wasting 1 cycle. But I don't like this at all because I'm wasting 1 cycle a lot of time. So hopefully I want to be able to achieve this. We can reduce this miss penalty. In other words, I want to increase my branch prediction accuracy. How do we do that? The first thing that we're going to do is that we're going to change our policy from not taken to taken. That will immediately switch the 30% to 70%, right? So that's an improvement. But there are lots of challenges in order to achieve this. And the reason that we didn't do this from the beginning was that we need to have the address. We need to know what is the next PC. And remember, since I want to keep the pipeline going, as I'm fetching the instruction, as I'm fetching this branch, I need to know immediately what is the PC plus offset going to be for the next instruction. In other words, I need my next PC now during the fetch state, right? So if I know it in the decode stage, it's too late because I already need to fill the instructions with 1 more instruction in the fetch, right? So if I have my fetch, decode, execution, memory, and write back, let's say I bring I fetch the branch instruction, and in the next cycle, my branch goes to the decode instruction. Now I need to fetch something new here, right? If I predict not taken in the past, it was easy. I fetch PC plus 4, and at this point, we know whether we make a wrong decision or right decision. So in the next cycle, this branch goes here. If we made the correct decision, then we just continue PC plus 4 and grade, and then PC plus 8 here. And then if we make an incorrect decision, we just scrap this and we fetch, instead of fetching PC plus 8, we fetch PC plus offset here, and we insert a bubble or something here, a no op here, and then we continue forward, right? So with a wrong instruction, with wrong, if we know at decode, we only replace the instruction with 1 bubble and we move forward, and that was great. But if I want to be able to predict taken, it means that at this point here, I need to know what is my next instruction. At the end of this fetch state here, I need to know my PC plus offset. Okay. I need to know that this is a branch, and I also need to know that this is what is the PC plus offset. And already you know that all these things we already have in the decode state, not the fetch state. So in other words, now I need to move things a little bit back to the fetch state. So let's see how we can do that. Is that clear? Anybody has any questions of why we're doing this? Yeah. Yes. So I'm going to have this sequence here. So fetch, decode, execution, memory, and write back. My branch is here. Okay. Now my branch goes here. And the question is, what should I put here? In the past, we told you that here we put PC plus 4. Okay, so option number one is that we assume that this is not taken. Then I'll put PC plus 4, whatever instruction is there, I'm going to fetch that and put it here. And great. And then another thing that we said is that at this point, if it's indeed not taken, then my branch going to go to the execution stage. My PC plus offset, my PC plus 4 going to go to the decode stage. And here I'm going to fetch PC plus 8. Okay? So this is, we predict not taken and it comes out as not taken. The other option is if I have fetch, decode, execution, memory, write back, I have BEQ, and now I fetch PC plus offset, PC plus 4, and now at this point I realize that I made a mistake. So the branch should have been taken. What should I do? I get rid of this. So I put a no op here. I continue my branch here. And what do I fetch here? I fetch PC plus offset here. So I waste one cycle by inserting a no op, but I'm good to go. Okay. So now what I want to do is that, can I somehow fix this issue? What I want to do is fetch, decode, execution, memory, write back. I want to have BEQ here. My BEQ goes to the decode. And what I want to do now, instead of PC plus 4, I want to be able to do PC plus offset. Can I do that? How can I do that? Okay, that's what I want to achieve, because I want, as soon as I see a branch equal or any sort of branch, I want to predict taken this time, not taken. So two things I need to do. I need to know that this is a branch, and I also need to know what is the PC plus offset. I need these two things. Okay, so how do I get this? So as I said, we're gonna need next PC at the fetch state, and I also need to know that this is a branch. Okay, so here's the idea that I'm going to do. I'm going to keep track of my previous branches, and I'm going to use that in order to predict future branches. And in order to do that, I'm going to also remember the addresses of those branches. Okay, so I'm going to maintain a table in the fetch state. And that table is going to tell me that if this branch has been visited before, what was the address that it used? Okay? This way, I'm going to achieve the following. If I see a branch for the second time, I know for sure where it jumps to. Okay? So I have what I want. I have the PC. I see that branch. I go to the table. I see that if that branch has been seen before. If the answer is yes, I have the address. Problem is solved. The second question is, what if I didn't see the branch? Then I will predict not taken for the first time. I'll pay the penalty of not taken, but I'm going to update my table with that branch and the address. Next time I'm going to see it, I know the address. So basically, my taken strategy would be a two-step strategy. At first, I'm going to predict not taken the very first time I see a branch, but I'm going to record that branch and its corresponding PC plus offset, this corresponding target into that branch, into that table. Next time I'm going to see that branch, now I have the branch and its address. I can predict that. I can move forward. Okay? That's the idea that we're going to implement. And I'm going to put this table in the fetch state. So as soon as I get the instruction, I can search my table and I can find the address. If I find the address, I have all we need. And that's all I need for the branch. I don't need to decode it. I don't need to use an ALU. I don't need to compare anything. It's just basically just a memory, just remembering what happened last time. If I know that this was a branch and this was taken, I have my answer. Okay? This is what we call a branch target buffer. Okay? So we are kind of guessing the next address based on this. Okay? So essentially the idea is this, that if we see a branch instruction before, we know where it jumped. As a result, we're going to remember this, and this time that we see it, we're going to jump there. Question? So the question is, what if the branch is not taken and we predict taken, right? So if it's a loop that always jumps back, but one time it doesn't jump back, it jumps somewhere else. So we're going to have misprediction, and we already know how to fix misprediction, right? So it's not going to be 100% accurate. Remember, we're going to do taken all the time, but taken all the time is also not accurate. It's only accurate on average 70% of the time. But we already have a mechanism for flushing. So if you see that we made a mistake, we're going to go back and fix it. Okay? So this actually answered the second question here. Yeah. Good question. How do we know that we see the same branch? So it will be the way that we're going to store the branch. We're going to save something in the table, and we're going to use it. So we're going to save some form of an ID for each branch. If you have a unique ID for each branch, then each time we check that ID. All right. So this is what we call a branch target buffer, or BTB. Okay. So branch target buffer is a buffer, or it's a memory that stores the branch targets, the address that the branch jumps to. Okay. Basically, what it stores is the target address, 32-bit value. This is the address of basically this is the value of PC plus offset, right? You can also store the offset and then add the PC to it. You can store it as a label. You can do whatever you want, but just you have to be careful of what you're storing. Typically, people store the final target address. In other words, the content of the table would be equal to PC. Okay, so the table would be the BTB table, whatever it is, going to be the value that PC gets. Alternatively, I can store the offset and then do PC plus offset, but that's also fine. But what I'm going to do is that question that your one of your classmates asked, and that is like, how do we store things and then how do we search through this table? That's the main question that we need to answer. So the design of this table has to be very carefully designed so that we be able to search this, and we need to search this fast. You other question? So the question is that what if you have like lots of branches stacked together? Remember, we always fetch one at a time, so we can always like read one branch at a time. So we're good. If this is like a super scalar processor that has many things at the same time, then we need to be careful about that. But since this is a pipeline processor, we always do one fetch, one decode at a time, so we can always keep pace with the table. You have a question? No? Okay, so what we're going to do in order to address this table is the PC itself. So imagine this. Imagine that I have a table as big as my instruction memory, okay? What I'm going to do is that I'm going to start by saying that essentially the address of my memory is the ID of my branch, okay? Since every single line of my memory is just one unique address, I use that address to ID which branch is which, okay? So the very kind of rudimentary solution for this problem is, this is my instruction memory. And remember, I had 1 byte, so like kind of like 4 bytes, this is one instruction. And then another 4 byte, another instruction, and so on and so forth, right? So that was kind of like the design of my instruction memory, okay? Here's what I'm going to do. I'm going to say that essentially each instruction, there is a one-to-one mapping between the address of an instruction and the instruction itself. So if you tell me the address, I can tell you the instruction. And that would be the unique ID for that instruction, okay? Not all of these instructions are going to be branches, but if I have a big table, and this would be my BTB, that essentially I index it using the address. So address 1 would be the first column, address 2 would be second column. The next time I see the branch, all I need to do is addressing the correct content, the correct entry in this table, and bring back the target address. So here I'm going to save the target address. So the content that I'm storing here is the target address. But the way that I'm going to address this is basically I'm going to use the PC. In other words, I'm going to use the instruction to address this table. Okay? That's the very simple way that I know uniquely which branch is which. And there is no overlap between them. Okay? That's one way of doing this. But that means that my BTB would be as big as my instruction memory, which is huge. Okay? And I cannot afford to do that. So what I do instead is that I'm going to reduce this to, let's say, divided by some number, n. Okay? Which means that I'm going to map n entries into 1. There will be overlap, which means that there will be branches that I think that I've seen before, but I didn't because only their addresses clashes. But again, that will just contribute to my accuracy. It's not going to create any issue in terms of correctness. But this way, I can reduce the size of my BTB. So instead of using the whole address, I'm using partial address to address this table. Okay? So this is what we're going to do. We're going to use lower bits of my PC to address this table. How many bits? Depends on how many entries you have. Log n of that would be the number of bits that I'm going to use. Okay? So for example, if I have 1,000 entries, I need the log of 2 of that, which is approximately 10 bits. Okay? So I need 10 bits, like lower 10 bits of my PC to address this table. You might ask, what if, for example, I have 1, then 10 zeros, and then I have 0 and then 10 zeros, or I have like 1, 1 and 10 zeros, or I have 1, 0 and 10 zeros. So these are two separate PCs, two separate branches. Both of them maps into the first line of my BTB. This is what we call a collision, right? There will be a collision between these two. This will cause an inaccuracy, but that's not a big deal. I'm trading off the area with some accuracy of my branch predictor. Yeah. That's a great question. So the question is, do I need all 4 bits or not? All the 10 bits or not? At some point here, I have that. But yes, you don't need the first 2 bits. Okay? So here's what we're going to really do. So remember that PC always was PC plus 4. So you always say that the first 2 bits has to be equal to 0. Right? Actually, we said that, okay, there are some instructions that we might have a 16 bits instruction, so essentially just the first needs to be 0. But if you assume that you always like instructions are 32-bit, these 2 bits is always 0. So I can safely ignore that, and I start my 10 bits from here. So I start from bit 2 to 12 instead of starting from 0 to 10, okay, or 0 to 9. Sorry, 2 to 11, right? The reason for it is that if the first 2 bits for all of them are 0, there is no information there to store, so I can just move 2 bits. If I want to also keep track of 16 bits, then I just get rid of 1 bit, because 1 bit is always 0, and start from 1. So you have these optimizations that you can definitely do. All right. So here's what we're going to do. And then now the second question is that if I want to partially use the PC, why not using the higher bits instead of lower bits? Okay? Because let's say if my PC is 32-bit, right? I have a bunch of different options. Why not I'm using, for example, from here to here? So why not the most significant bits as my address? And then just ignore the lower significant bits. The reason for this is what we call locality. Okay? If you think about the difference between this option and this option means that we are kind of distinguishing instructions that are next to each other. So this instruction and this instruction, the difference between them is just 1 bit difference of PC, versus if I look into this higher bits, the difference between 2 consecutive instructions are large areas in the memory. Okay? The reason that I want this instead of like this big differences is that what we call the working area of a program is usually small. So you usually just working within few next instruction next to each other. Like you have a for loop, you have a while loop, you have a function. You have instruction next to each other, which we call locality, spatial locality in this case, which means that they are next to each other. I want to be able to distinguish these next instructions to each other from each other. I don't care whether this instruction and very far away instructions are different or not. I care about these next few instructions to be different from each other because the branches are happening here. So I want to be able to distinguish these from each other. That's why we call this locality, and that's why we use the lower bits to be able to exploit that locality from my system, okay? So I want to be able to say that if this is a branch and then let's say here is also a branch, I want to be able to absolutely distinguish the difference between them. And if I see the addresses, you will see that the lower bits is where the difference between these two are. The higher bits are all the same for these, okay? If I didn't use the lower bits and high bits, then I wouldn't be able to distinguish the difference between two next to each other branches. And that's why we are using this. Yeah, you had a question. Oh, yeah. The question is why collisions are not a problem. Collisions is a problem. What happens is that if I have a branch and then another branch that happens to have the same lower bits, what's going to happen is that, let's say I see this branch and store it in my BTB, okay? Then the next time I see this branch and I think that I saw it, right? So I'm going to go to this and use the target address. What will happen is that if this was for this branch, I'm going to just use a wrong target address. In other words, I do a misprediction. And I can fix this by just flushing this out later time. So if I find that, oh, these two branches are not the same later on, I'm going to show you how, I just flush this out, same issue that we had with not taking. So it's just, again, a misrate issue, not a correctness issue. I'm going to show you how we detect. So essentially, in order to detect, I need to store the full address at some point. So the question is, if I assume that branches doesn't happen 4 at a time, then I can like also leave off like third bits as well, right? And then I can keep doing this. You can do these optimizations. Typically, we just get rid of the first two because there's a possibility that you have back-to-back branches and JALs. But yes, you can do those optimizations. Yes. The content you mean, or the address? So yeah, so here's what's going to happen, right? So I have a sequence of instructions, like this is my PC, and I have a branch equal here. This is my PC plus. Let's say my PC is equal to, let's give you a number. So let's say my PC starts at address 100, and I have an add instruction here. Then at 0.4, 104, I have my BEQ here, okay? And this BEQ is like X1, X2, and address, I don't know, 0x300, okay? So what we're going to store is we're going to take this instruction here, okay? And we're going to do this. We're going to use the address, which is the PC. So 0x105 is my address, okay? I'm going to take whatever mapping that I want to do. For example, I'm writing this into binary, and I'm going to take, let's say, bits 2 to 9, okay? Whatever that number is. That would be the address that I'm going to use. This would be my address of the BTB table, okay? Then I'm going to store, so let's call this Y, okay? Then I'm going to store this number, or if I want to store PC plus offset, then I'll do that. So I'm going to store PC plus offset into BTB Y. Okay? That's what I'm going to do. So I find the index of that array, that table. In order to calculate that index, I use the PC itself of the branch. I have a different mapping. I might use the first 10 bits. I might use the last 10 bits, whatever it is. I'm going to extract that. That would be the index of that table. Then what I'm going to store there is the PC plus offset, which is the target address of this branch. Okay? Any other questions? All right, great. So going back. So as I said, the reason that we want lower addresses is what we call locality, in this case, spatial locality, which means that closer addresses are relevant to each other, so you won't be able to distinguish them from each other, okay? So here's the algorithm that we're going to use, okay? For a new PC, for an instruction that we see and never seen before, we record the target address into the table. How do you know that this is a new instruction? Because it already doesn't exist in my table. So the first thing I'm going to do is search. If I don't see it, I'm going to record it there. What I'm going to store is the target address of that, okay? Next time, for a recurring PC, I'm going to look up, and I'm going to find that because I already stored that somewhere in the past. Then what I'm going to do is that when I see that the same index, the value already exists there, I'm going to take that value, and that would be my target address. That would be my prediction for my brand. So my next PC would be whatever is stored in that address. So in this case that I gave you, the first time I'm going to do this, but since this is probably some form of a loop or something that sometimes it's going to go back, then second time I'm going to do this, I'm going to see this. I'm going to calculate BTBY. I'm going to see in BTBY that, aha, I already stored this value. So this would be my next PC. Okay? Yeah, other question? Great question. So the question is, wouldn't this be very expensive? Because essentially every single cycle I need to read something from memory. That's why BTB has to be very small so that it fits on the chip. Okay, so I'm going to have a very, very small memory that's very fast. Remember that I said we have different types of memory. If it's big, it goes outside, it would be SRAM and DRAM and disk and all. I want to essentially my BTB to be some form of a register file so I can address within one cycle. So my BTB is combination of flip-flop. It's not like a real SRAM or DRAM. So it's fast. It's within one cycle. That's why I cannot afford to have a big BTB. If I could, then I would have better system. Yeah. Two reads. No, it would be one read. So you're going to see whether it's there or not. If it's there, you already read the target address. Boom. If it's not there, then you don't predict taken, you predict not taken. And then you later on go back and fix it in the background. You don't need to, that's not a part of your critical path.
Are you reading the actual instruction, or you just read the actual C plus offset?
Oh, you two reads? Yeah. So you fetch from the instruction memory, that's one read. You read from BTB, that's another read. But you read this in parallel because you have the PC for both. So actually your design is like this. So you have your PC, you read your instruction memory, you also read your BTB at the same time. So two separate reads, what happens in parallel. So your critical path is not going to be increased. Yes. The BTB what? Overwritten, of course. So the question is, does the BTB overwritten? And yes, if we have those collision scenarios that you have two PCs that maps to the same line, then they will overwrite each other. Question, yeah. The question is, this happens for every instruction? Yes. Even for non-branch instruction, this happens. Because at this point, I only have PC. I have no idea what this instruction is. I'm going to just go and grab things from BTB. Good thing about non-branch instructions is that they're not going to be there because I never updated my PC with non-branch instructions. But this read happens for every single instruction. Yeah. The question is, what if there is a collision between a non-branch instruction and a branch instruction? That's a great question as well. It might happen, but again, that might be if it's a branch instruction, you read this value, read this next PC, and again, at some point you will realize that you made a mistake and you can recover from it. Yeah. All right. Good. Okay. So let's pause here. Then later on, we're going to talk about the details of a BTP and how do we fix these other issues, as we said.